Good morning, everyone. Welcome back for Calc. I just want to dive straight in and start this section 17.3 on conservative vector fields. In this case, we're using the word conservative more like it's used in physics or engineering, namely something is conserved as in nothing is created or destroyed. So this particular section is interesting. It's an action-packed section in which several fundamental ideas come together. At the heart of the matter are two questions for us. When can a vector field be expressed as the gradient of a potential function? A vector with this property will be defined as a conservative vector field. And then also, what special properties do conservative vector fields have? So in this section, we present a test to determine whether a vector field in R2 or R3 is conservative. And the test is followed by a procedure to find what's called a potential function for the conservative field. And we'll also develop several equivalent properties shared by all conservative vector fields. So I'd like to just dive straight into the notes and start understanding what is meant by a conservative vector field. So again, this is section 17.3 on conservative vector fields. So recall that given a function f of xy, we can find the corresponding gradient field nabla f. The following definition reverses this relationship. So just to be clear, what I mean by reverse is that in the past, we've started with f of xy, and we've used it to find that gradient field. So a conservative vector field. A vector field f is said to be conservative if there exists a scalar function phi such that f equals the gradient of phi. So it's conservative if it's a gradient field. Very cool. All right, so there are a number of important conservative fields in physics. Many of you are taking physics and engineering. What are conservative fields or conservative things in physics?
Gravity.
Momentum.
Gravity. What was the second one you mentioned?
Momentum.
Momentum is conserved. What else? Is there stuff around E and M? I can't remember. Electricity and magnetism. It's conservative.
Electric field.
Electric field. I'm pretty sure that there's at least one in there. Anything else that you can think of?
Energy.
Energy. Yeah, that's the big one. It's actually the one we'll talk about in this section. So there's all these conservative fields in physics, and we want to understand them better. Just to be clear, if you've had physics, I think that you'll find some nice connections here. And so I think you'll enjoy that particular part of the section. But for those of you that have not had physics, I think you'll be just fine. The math stands on its own. You'll just sort of miss a little bit of the beauty wonder of the whole situation. So there are a number of important conservative fields in physics which prompts us to want to understand them better. As you may recall from Clairaut's theorem back in Calc 3, if a function has continuous second partial derivatives, the order of the differentiation in the second partial derivatives does not matter. So here, notice you have the partial derivative with respect to x, then y, and that's equal to the partial derivative with respect to y, then x. This leads us to the following test. So a method to test for conservative vector fields. There's lots of complicated things in this section, but there's one really easy thing, and this is the easy thing. So let f equal to fgh be a vector field defined on a connected and simply connected, connected and simply connected region D of R3, where f, g, and h have continuous first partial derivatives on D. Then f is a conservative vector field. That is, there's a potential function if and only if one of these conditions is true. So here's the condition in R3. in R3. And here's the condition in R2. R2. All right, I want to just double check one thing to see if there's a typo in my notes, because I've connected and simply connected, which seems a little bit redundant. I feel like I'm missing something. Oh, that's right. Yep, that's correct. All right, sorry for the pause there. Let me just pause and talk about these terms. So this idea of connected, of simple regions, et cetera, this ends up being important, but all the examples that we work with in class tend to satisfy them. So there's like a whole bunch of fine print here that's important, but doesn't end up coming into play a lot other than making things more precise. And so what I did was I posted a video about this stuff. So there's a separate video that's about these things, about kind of the regions.
Is there like a really quick explanation of
like
these two terms?
Like some of the
Just like
stuff,
a little...
yeah, like the short version. So some of the stuff means things like your regions can't be like this, where this can't be both D. This would be an example of something that is not connected. So this is not connected, or it can't be like a donut with a little. Like that would probably be some of the short version. It's a good question. So again, did that help, Croy?
Yeah, it did.
Very good. Okay, so going back to these conditions, the nice part about these tests is they're really easy to run. You just test some partials. Again, if you want to know why these conditions are the way they are, it's easiest to think about where they would come from. So imagine that F is conservative. So if you had F conservative, so this would be saying that it's equal to some gradient of phi. And so that would be telling us that big F would be equal to like the partial derivative of phi with respect to x, partial derivative of phi with respect to y. So this is how you find the gradient itself. And then here, I'm taking, just make sure it's clear. So we're saying that the little f would be like phi x, g would be like phi y, h would be like phi z. Phi z sounds like a name. And so the partial of f with respect to y, this would be like the partial of f with respect to x, because that's what the f is. And then with respect to y, so we take a second derivative. And partial derivative of g with respect to x, well, we're going to start with g. So that would be partial derivative of phi with respect to y. And then we can take the partial derivative of that, come on little buddy, with respect to x. And so you see, oh, this condition is just an extension of that Clairaut's theorem that we were talking about earlier. Questions about this? Very good. So what I'd like to do next is work through an example. All right. So in this example, we're given this field F and asked if it's a conservative vector field. And so in this particular case, the first component, this would be our little f. Second component would be our little g. And so we've got to start with our test, which should be find out whether the partial of f with respect to y is equal to the partial of g with respect to x. So to do that, partial of f with respect to y is equal to, looks like to 3.
3.
Yeah, happy 3. And partial of g with respect to x,
3.
also 3. So what can we conclude from that?
It's a conservative vector field?
Yeah, exactly. So F is conservative. All right. So F is conservative. Great. What does it mean to be conservative? What would be another way of saying conservative? It means that F is a what?
Simply connected region?
Nope, simple. It's a type of...
It's a gradient field,
It's a gradient field, exactly.
which also tells us that it's continuous and that we can find a potential field from it.
Exactly. So since it's a gradient field, the next thing we want to do is we want to find the potential function. Questions so far? Very good. All right. So, and we're going to label this potential function phi, just so that way when you start seeing phis running around, you know what they're about. So we want to find that potential function. Find phi. So to do that, we're going to start with our, there's a whole bunch of steps here. So the first step is we're going to start with f with little f equal to 3y plus 4. And we're going to integrate WRT with respect to x to find phi. Okay. Remember, a gradient is like a derivative, so if you want to find the potential function, you need to anti-differentiate. So we integrate 3y plus 4 with respect to x, and we get out 3xy plus 4x. And then what else do we need?
Let's see sub 1.
We need a constant, but it's a special kind of constant.
It's going to be our function.
Yeah, it's a constant with respect to x. And so it could have which variable in it?
Y.
It could have y's in it. Let me see if I can make this. So this cy right here is a constant with respect to x. Okay, so we integrated, we found our potential function phi. Maybe it's not clear. So we're saying that phi of xy is equal to this thing. So phi of xy is equal to 3xy plus 4x plus cy. Well, I think we still need to figure out what our cy is. So the second step is we need to differentiate differentiate phi of xy now with respect to y. And so we're going to take the partial derivative with respect to y of 3xy plus 4x plus c of y. And so what's that going to be equal to?
3x.
X.
With respect to y. This is a 4.
C prime of y.
Oh, sorry.
Yeah, it's okay. My handwriting. C prime of y. Okay. And this thing, the derivative, what do you call the partial derivative of phi? Remember, this is our potential function. The partial derivative will be the y component of the original field. So all this stuff is equal to g. So this is equal to 3x plus 5. Let me make sure you can see what's going on. So here's our g. Like this. There it is in the light. So here's the partial derivative we just found. We set it equal to our g that we were given. And so this tells us that c prime of y is equal to what?
5.
To 5. Okay. So do we know what phi is yet?
We're
No.
getting there.
We're getting there, right? Because we have this formula for phi. Phi is equal to 3xy plus 4x plus c of y. And we now know what c prime of y is. So next step, 3, we can integrate c prime of y. And so we'll get integral of, I think it's 5, right? Oh, and this would be with respect to y. Complicated antiderivative, you're going to get 5y plus a constant, right? Maybe I'll use k for the constant. Okay. And so this lets us state our conclusion that we get phi of x comma y is equal to 3xy plus 4x plus 5y plus k. Most of the time we like to just ignore this k. And so we're gonna ignore the real constant. And so we'll say just that phi of xy, this is our potential function, is 3xy plus 4x plus 5y. Recall that f was equal to 3x plus 4 comma, 3y plus 4, 3x plus 5. What's the relationship between these two?
They're not the same?
True, they're not the same. Like, what's the relationship between what we started with and what we ended with?
Well, we went from our gradient field to the vector field that it's associated with.
Yeah, so this is the gradient field nabla phi, and this one up here is called the potential function. Questions? I don't think I can get you the whole actually, I could probably show you all the notes if I switch over to my pre-done notes. So here's that whole solution. Questions about the process? Have you found potential functions in other classes? I feel like maybe this happens in differential equations.
Yeah, we touched on it towards the end of differential equations.
Okay. All right. Okay, I'm going to give you a step-by-step list version of the process, but let me just show you what happened in a picture form. So we started with little f, and then we integrated, and this found us our first version of phi. And then we differentiated, and we compared to g. And then we integrated, and we found, so this also gave us our c prime of y. And then we integrated again, and this got us our final phi. And this first one had with the constant c of y. So you integrate, differentiate, integrate. It's like a back and forth process between the two. In the notes, the way I lay this out is as follows. So you're going to integrate, and then you're going to differentiate, and then you're going to integrate, and then you're going to differentiate, and then you're going to integrate. And in this particular case, I did the 3D version, which has 5 steps, versus the 2D version, which just has 3 steps. So I'd like to do one of these more complicated versions, but before we get there, are there any questions? All right, so let's look at one more example. And it's long, and the reason it's long is because I wanted to make sure that every step counts. So same type of question as before. We have this field, and we want to, first thing we want to do is we want to determine whether or not it's conservative. And so since we want to determine whether or not it's conservative, we have that 3-part test. Remember, this is the more complicated test. So we could find the partial of f with respect to y. So here's our f, it's the first component. So we'd get z plus 2. And we'd ask, is that equal to g of x? And so g of x would be z plus 2, so this is g of x. And then we also need to test fz. Partial of f with respect to z would be y.
You mean hz?
I don't think so.
Oh.
Let me switch. So I'm using this test right here. So I have fy equal to gx, fz equal to hx, gz equal to hy.
Oh, okay. Sorry. Thank you.
No problem. So fz would be y plus 3, and this is indeed equal to hx. And then last but not least, we got to check GZ. That's equal to x plus 4. And then we check this against HY. And sure enough, those two are also equal. So we got all three of these statements are true. Therefore, that tells us that G is conservative. That is, G equals to some gradient of some potential function phi. Whew. So what is that potential function? So to find the potential function, we start with f equal to yz plus 2y plus 3z plus 5, and we integrate. With respect to x. So yz plus 2y and all this stuff is going to be equal to phi of xy. So antiderivative of yz would be xyz, 2xy, 3xz, plus 5x, plus we need
with respect to x.
yeah, we need a constant here, right? So we need and our constant is going to be a constant with respect to x. So which variables go in our C?
Y and Z.
Y and Z.
Shouldn't our phi be a phi of x, y, z?
Ah, got it. Good call. So this is, thank you. Appreciate it. All right. So we've got our phi, but it's got this ugly constant function that we've got to figure out. So we integrated. Step 2, we're going to differentiate with respect to y. So when we differentiate this thing with respect to y, we're going to get xz plus 2x plus 0 plus partial derivative of c with respect to y of yz. And we're going to set this thing equal to our g function, which is xz plus 2x plus 4z plus 6. So we're setting it equal to the second component. So this gives us partial derivative of c with respect to y of yz is equal to 4z plus 6. Whew. We integrated, we differentiated. So what do we do next?
Integrate our cy.
We integrate our cy. So step 3, we need to integrate the partial derivative of c with respect to y. So the integral of cy will be the integral of 4z plus 6 dy, which would be 4yz plus 6y plus a constant. We already used c, so I'm going to use d. And this has to be a constant in terms of x and y, so this would just be a function of z. And so just to summarize where we're at so far, we know that rho of x, y, z would be equal to xyz plus 2xy plus 3xz plus 5x plus, and now here's our new c function, 4yz plus 6y plus dz. So that's the end of step 4, sorry, to step 3. So for step 4, we need to differentiate and now we're going to differentiate with respect to z. And so we'll find our phi with respect to z. And so this will be xy plus 0 plus 3x plus 0 plus 4y plus 0 plus d prime of z. Notice now it's a prime because there's only one variable. It's not no longer a partial derivative. And we can set this equal to our h function, which I lost track of. Our h function, which is xy plus 3x plus 4y plus 7. Here, that h function that we were given right at the outset, we're setting equal to this partial derivative. And from there, you should be able to see that the xy's and 3x's and the 4y's match. All that's left is d prime of z equals 7. So this tells us that d prime of z equals 7. So last step, we need to integrate d prime of z with respect to z. So we'll get the integral of 7 dz, which would be 7z. We talked about it after the last example that we don't need to include the true constants of integration, so we'll just leave it at 7z. So this allows us to put everything together all at once. So we get that rho of xyz is equal to xyz plus 2xy plus 3xz plus 5x plus, let's see, lost track of some of those previous results, plus 4yz plus 6y plus 7z. So this that we just found is the potential function for the gradient field, G, which was right at the outset of our question. That ugly thing that we started, yz plus 2y plus 3z plus 5, comma, like that. And again, the process that we used was, in terms of process, was we started with our function g equal to f comma little g comma h. And so we started with f and we integrated with respect to x. And so we got our row function, but this one had with a constant c of yz. So then we differentiated, and so we found the derivative now with respect to y. And so we solved g equals phi with respect to y. And this let us find, this gave us the partial of c with respect to y. Then we integrated with respect to y. And so now we found phi with constant d of z. And then we took the partial derivative. Actually, this is a straight up derivative, not a partial, with respect to z. And so we solved h equals to phi, partial derivative of phi with respect to z. And this gave us d prime of z. And then we integrated that with respect to z. And we found phi, our final potential function. So here's your start. You came down via integration. Then you came back via derivatives. And then you came down again via integration. And then you went back via derivatives. And then one last time you did integration. So it's this integrate, differentiate, integrate, differentiate, integrate to get your final result. And that's the end of the example.